This is part 2 of a video about convergence of series. So I'll start with a useful result that we could use to prove that a given series converges. So here's the result. So if you've got a sequence xn and where all the xn's are non-negative real numbers, then the series xn converges if and only if the sequence sk of the partial sums is bounded. And furthermore, what does the series converge to? It's the limit of the partial sums, of course, but it's the supremum of the partial sums. So how would we try to prove this? So what are we assuming? We're assuming that our sequence always consists of non-negative numbers, so xn is greater than or equal to 0 for all n. So that tells us then that the partial sums are monotone increasing, right? Like when you go further out in the partial sums, you're just adding more and more of these xn's. Therefore, again, you're adding more and more. Those are positive numbers. For each partial sum should be getting bigger as well. So in particular, monotone convergence says that sk converges if and only if it's bounded. So since sk is monotone, it'll converge if and only if it's bounded. So maybe what we'd like to do is just show that the sequence of partial sums sk is bounded, right? But furthermore, or I guess that's it, right? So we just showed that it converges if and only if it's bounded. And if it converges, it's increasing and it's bounded, then what should it converge to? Which should converge to the least upper bound, right? Which is the supremum. So how would we try to show that something like 1 over n squared, adding up all those types of numbers, like 1 plus a half, 1, plus a fourth, plus 1/9, plus 1/16, etc. How do we show that converges? So let's let sk be the sequence of partial sums for that series. And maybe note first, sk, it's monotone increasing because, well, xn is 1 over n squared. There should be a squared there, of course. And that's always non-negative for all natural numbers n. So by the above, it would suffice to just try to show that the partial sums are bounded. So in that case then, it suffices to show, in fact, that some subsequence of the partial sums is bounded. And maybe you're wondering why that's so. Well, suppose that we had some subsequence that is bounded. Say its indices are k1, k2. So what does that mean? There exists some real number that's positive m, where m is bigger than all the terms in your subsequence. That's what this is trying to say here. But what do I know? For any natural number j, though, I know that j should be less than or equal to whatever term that denotes in my subsequence. It's less than or equal to kj, and that's a result we talked about before. But then what else do I know? Well, I know that the sequence of partial sums is monotone increasing. So in particular, the jth partial sum should be less than or equal to the kjth partial sum because you're farther out in the sequence at kj than you are at j is what this says. And again, that's because sk is monotone increasing. So that is just to justify that maybe we could get away with looking at a nice subsequence of this to show that it's bounded in order to conclude that sk itself is bounded. So in particular, what should that nice subsequence be? And so let's let k1 be 2 to the first minus 1, which is 1, so that sk1 is 1. So sk1 is 1 is the first term in my subsequence. Let's let k2 be 2 squared minus 3, or minus 1, and you get 3. So I'm saying that sk2 is just equal to, should be a 3 right there. K3, I think you see the pattern. It's going to be 2 cubed minus 1, so I'll write that down. So 2 cubed, oh, sorry, I wasn't quite done with that. So sk2, oh, I see what I was saying there. No, I was quite right. sk2 is s3. How come? What am I saying to you there? k2 is 3, therefore sk2 is s3. But now, like, what is s3? That says add up the first 3 terms of this series here. So 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. All right, I see what I'm doing now. Forgot for half a second. So these are the first 3 terms in your series, and what we're going to do is we're going to conveniently bound those. That's less than 1 plus, well, 2 over 2 squared, which is equal to 1 plus a half. So far, I'm telling you that sk2 is less than 1 plus 1/2. Let's do another one, k3. So I think you see the pattern should be 2 to the 3rd power minus 1, so 7 here. So what we're saying is that the next term in my subsequence is just going to be the 7th partial sum. So I want to think about that. And so, I mean, what would this be? Well, 1 over 1 squared. Keep going out until you get to 1 over 7 squared, right? But I'm going to write that as sk2. I've already got the first 3 here. That's sk2. Plus the next ones, right? Those would get me up to 1 over 7 squared. And now I'm going to play the same kind of game here where each of these, well, there's 4 terms in here, and that sum is less than just 4 over 4 squared. And in particular then, what was SK2? Remember, SK2 was less than 1 plus 1/2, and so I'll just plug that in right here. So far, SK3 is less than 1 plus 1/2 plus 1 over 2 squared. And so this is all kind of a trick. If this doesn't seem natural, this comes from a lot of playing around with stuff. But what's the point that we're trying to do? The point that we're trying to do is to show that by induction, what can I say about SKJ? Well, it looks like it's going to be less than a bunch of sums, a sum of a bunch of powers of 1/2. And so in particular, like how many do you have? Well, whatever j is, you have j minus 1 powers there. So what do I mean from that? How can you see that? Let's say j is 3 here. Notice last power 2 I have is 3 minus 1. That's this here. Hope it makes sense where that comes from. But anyway, why is all this done? What are we doing? What's the point of this? This is a partial sum of a nice geometric series where r is 1/2. And I know a lot of good stuff about a geometric series when r is 1/2. I know what it adds up to. It adds up to 1 over 1 minus r. So in particular, what have we got? We've got that skj for any j is always less than 2. So what does that show? That shows that this subsequence of partial sums of 1 over n squared is bounded. And what we said around here is that it's, I guess I said it here. If you can show me that a subsequence of sk is bounded, which we just did, then it follows that the whole sequence sk is bounded. So to tie that back in. So skj is bounded, thus sk is bounded, and by the above result, remember that a monotone bounded sequence is convergent. Cool. So pretty similar arguments to that. In fact, what you could show is a stronger result, which I won't go too much into detail with, but we'll call these P series. So what we just looked at was called a 2 series, where P was equal to 2. And maybe you remember this from Calc 2, say, I know that this series, 1 over n to the pth power, converges if and only if P is larger than 1. So that is useful. The next things that I want to tell you about is comparison test. So what's the comparison test say? If you've got 2 sequences where, what am I assuming? At some point, the yn should be bigger than the xn's, and what I'm also assuming is that eventually all the terms in the sequence become non-negative numbers. Then there are 2 things that we could say for sure. If the big series converges, right, big series since yn is eventually the bigger terms, so if those converge, then that implies that the smaller series xn converges. That's how I'll think about that. Help me remember it. And then similarly, if the smaller series, right, smaller because eventually the xn's are always less than the yns, if that diverges, then anything bigger than it should diverge too, is what the logic says. So how do you show that? Let's try to show number 1 here. So suppose that yn converges. Remember what that meant? We had like the Cauchy criterion that says what it means for a series to converge. So for any epsilon, you should be able to ensure that the partial sums, the difference in the partial sums is less than epsilon. So given epsilon bigger than 0, we should be able to go far enough out in the series, in the sequence of partial sums, right, such that once you go past that magical number capital M, the difference in the partial sums, so in that case, this is like y1 plus blah, 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 plus ym minus y1 plus blah, 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 plus yn. If you were to do that subtraction, you notice that a whole bunch of stuff's going to cancel, and if m's bigger than n, then the yns would go away. So the first thing you'd have left is yn plus 1, right? What's the term after that? Up to ym. Hope that makes sense where these come from. So we want to get used to that this is just kind of very quickly what the difference of partial sums look like. Anyway, that's less than epsilon. So I got to push this a bunch of times. Bear with me. Almost there. There, cool. All right, so why don't we let n be the larger of that m that we just talked about that ensures that the partial sums of the y's are less than epsilon. The larger of that, and k. And what was k again? K is what ensured me that the y's are bigger than the x's. So if I just go past both of those numbers, then you could tell me that the partial sum of the x's is less than or equal to partial sum of the y's. Absolute value here is a little bit redundant since these are assumed to be non-negative once I get there. But anyway, that's all less than epsilon. So the point again, well, the partial sums of the x's are less than epsilon eventually. Therefore, the series xn converges. So that is how number 1 goes. And if you look very carefully at what is part 2, part 2 is really just this part 2, that's just the contrapositive of this. So therefore, I don't need to do any more work. We have both results. So that's the comparison test. The other very popular one we'll use is the limit comparison test. And so if you have two sequences that are strictly positive, so all the terms in there are strictly positive numbers is what it's saying, and let's suppose that R is the limit of that ratio xn over yn. Well, if R is non-zero, then what we can say, well, I know that the series xn converges if and only if yn converges. And so how you should read that is that xn diverges if and only if yn diverges also. So read this as both series xn and series yn have to have the same behavior. And if R is equal to 0 and if the series yn converges, then xn has to converge also. So that's more of a special case. So how does this look? How does this proof go? So let's try to prove this here. So what we're going to do is we're going to, again, play with this fact that I've got a limit here. So there's an epsilon definition to a limit, right? Eventually, I should be able to go far enough out so that for any epsilon you give me, xn over yn minus r is less than epsilon. So that should work for any epsilon, right? So what if epsilon is r over 2? Well, I should be able to go far enough out, so there should exist some capital N, such that once I go past that index, I should be able to make sure that xn over yn minus r is less than r over 2. The distance between xn over yn and r is less than r over 2. If you were to parse out that inequality there, and we'll add r to both sides, this should feel kind of familiar to something we did in a previous video. I've got that xn is between this multiple of yn and less than that multiple of yn. And so now what are we going to do? If we assume that yn converges, well then so does any multiple of that series yn. And in particular, we could pull that 3r over 2. It could come past the summation symbol since 3r over 2 is a constant. So why is that good? Well, here I've got 3r over 2yn is bigger than xn, and now I can use the comparison theorem, which tells me that if the big series converges, then the small series has to converge also. Cool. So the other way now, if xn converges, so xn converges, what does that tell me? That tells me, by the comparison theorem, or I guess maybe I'll get to that, so does any multiple of the series xn. So why don't I multiply by 2 over r, and you maybe see that coming from here. If you try to get yn by itself, hey, that would have a 2 over r right there. And in particular then, what have you got? You've got that this series yn is less than this, and again, the big series converges, therefore the small series will converge as well. And that's the next line. So that proves number 1. Part 2, what if r is equal to 0? Then we'll apply that epsilon definition again, where we'll take epsilon to be 1. I should be able to go far enough out in the sequence to make sure that the terms are within 1 of 0. So I should be able to go far enough out in the sequence so that the terms are within 1 of 0, is again what that says. And if I was to parse that out, what else do I know? I know that these are always non-negative, so I don't really need to put -1 on this side. I'll just put 0 over there, and I can make sure those are less than 1. And I'll just move yn over. And so xn is just less than yn. And so now again, by the comparison test, if the series yn converges, then the smaller series xn has to converge as well. And that's the next line. And that ends that proof. So let's just do a few examples that illustrate each of these theorems. So something like series 1 over n squared plus n has to converge. So how come? And what you want to maybe do is try to compare 1 over n squared plus n to something that you know about. And something that we know about are p-series. I know that if I was to take a little bit away from that denominator, something with a smaller denominator in the same numerator is going to be bigger than this guy here. So that kind of thing is something you'll do pretty often. And why is this good? We know that this series 1 over n squared, so this series 1 over n squared is a convergent p-series. Therefore, any series that's smaller than that has to converge as well. So that was the comparison test. So something like series 1 over n squared minus n plus 1 has to converge. And maybe you want to try to do the same trick where I'll just compare it to 1 over n squared. You got to be careful though, because here you're taking some away from the denominator also, and then you're adding 1. And so this inequality is not true, right? So you've got to be very careful. If you've got a bunch of plus signs in the denominator, then you can start deleting stuff without worrying. But if you've got some minuses in there too, you've got some thinking to do, and you've got to be careful. So let's not use the comparison theorem. That seems too hard to try to nail down what to compare to. So I'm saying it's not okay to compare to 1 over n squared here. Let's try the limit comparison test instead. So what we're going to do is I need to tell you about two sequences, xn and yn, and one of the two ought to be the one that you're posed with here, that you're asked to show the series with those terms converges. So I'll let that be yn, and what I want to do is I do want to compare to this sequence 1 over n squared. So what we're going to do is we're going to look at this ratio xn over yn, and if you simplify your fractions, you should get n squared minus n plus 1 over n squared. You can split that up into 1 minus 1 over n plus 1 over n squared. And so now if you apply that limit, both of these go to 0. So the limit's equal to 1. So that's like your r from the limit comparison test. So what does this say then? Since we got a nice number here, that tells me that the series whose terms are 1 over n squared has to do the same thing as the series whose terms are 1 over n squared minus n plus 1, which, hey, that's my series. So what do I know? I know that, well, this series converges, and therefore by the limit comparison test, if I go back up, xn converges if and only if yn converges. So again, what we're doing is we're trying to justify that this series and my series have the same behavior, which means it converges. And that again is the limit comparison test.